Hello everyone, so welcome to this session dedicated to the physical layer. So during this session we will have three interesting presentations that reflect the innovation in the physical layer of automotive Ethernet. So we will start by the first presentation titled Runtime Detection of Marginal Automotive Ethernet Physical Channels. This topic will address how real-time diagnostics can identify defect detection. So it will be delivered by Ian Hartwig, so from Zūks. He is system lead at Zūks. His work includes determining on-vehicle monitoring functions needed across network devices and following these throughout the specification, implementation, and verification flow. He will be joined by Anneka Noe, a member of Zūks hardware software integration team, who develops verification tools focused on automated testing and diagnostic. So the stage is yours.
Awesome. Thank you for the intro. Good morning. Welcome to day 2. We're here from Zūks to discuss detection of marginal automotive Ethernet physical channels, or put another way, which link in the vehicle dropped my data. I'm Ian, and joining me on stage in a moment is Anneka. Excellent. I almost walked on without the clicker. We'd also like to recognize some contributions from our colleagues, Austin and Sahas. Anneka and Sahas work in the hardware and software integration group. And Austin is our vehicle network architect specializing in Ethernet, and I work in vehicle network integration for Ethernet. A quick overview of our topics today. We'll review the Zūks vehicle services Ethernet use cases. We'll also look at some of the issue detection mechanisms we use for where the data is lost in the vehicle. We'll talk about verification methods for those issue detection mechanisms. And then we'll close the loop with some experimental results. Before we get there, what is Zūks? We're building mobility as a service via the Zūks autonomy software running on top of a purpose-built vehicle platform. A lot of the components in a Zūks vehicle are likely very familiar to folks in the audience. So we have sensors such as LiDARs and radars, and those are connected with 100 base T1. We have a variety of network switches and vehicle controllers on either 100 or 1000 base T1. And the Zūks autonomy software is running on a high-performance computer that is connected amongst those with 1000 base T1. Looking at this another way, however, clarifies our motivation to detect the marginal physical channels and also fix them. We both design the vehicle platform, and we also operate the service. So our mobility service customers would really like to have smooth trips all the way to their destination. And this relies on the automotive Ethernet links functioning as much as possible. When a vehicle detects an issue, however, we need to be able to pinpoint where that happened so our service technicians can take the appropriate actions and return the vehicle into the operating fleet as quickly as possible. So accuracy in detecting where an issue happens so that we can take appropriate action is great for the customer experience, and it's also very important for our business. Which brings up how does our engineering team usually get looped into something like this? Often we would get a ticket that reads like, the sensor data is unavailable at the sensor driver software running on the high-performance computer. So thinking about this in terms of OSI layers, which some of the presenters yesterday were talking about, this is more like layer 6 or 7, so like application layer, where the data didn't receive the final, get to the final receiver. There's also a number of indicators that we can look at in the lower layers to try to sort out why it didn't get to the end and correlate. Particularly, we would like to talk today about some layer 1 and 2 metrics like link state, ARGs, error counters, and SQI. Before we get there, though, some interesting failure cases that we've seen to spark everybody's interest. These are all things that we have seen across the vehicle platform. If there's a picture here, it's definitely not in the operating fleet anymore. But we've seen things like bent sockets turn into bent pins on connectors, water ingress into sealed connectors, mismatch between potting compound and thermal cycles. And all of these were rather difficult to see by visual inspection, yet clearly show up in diagnostic logs as missing data. So zooming in on what makes each of these cases, though, an operational issue, we can classify them by the lost duration of data on the link. And I'll refer to these as roughly transient, short, and long losses. So the 10 millisecond difference is related to a little bit to our sensing requirements, and it's also related to some capabilities of which verification tools we were able to build, which is what we'll talk about in a little bit. The middle category from 10 to 200 milliseconds, this actually has caused the most discussion internally for us. It turns out that this is long enough that it causes issues in usage of the sensor data, and so it really must be serviced on the vehicle. Yet it can also be a challenge to detect when we take into account the entire plumbing from underlying metric to logs and diagnostics. So this is the same categories with some of the detection techniques that are available. So we can see that there's actually quite a few for that transient category. There's been a lot of really good focus on this previously. That 10 to 200 millisecond category, however, is a little bit tricky. And it also depends on whether we're talking about 100 or 1,000 base T1. Particularly that on 100 base T1, we found that we needed to use the false carrier signal, which propagates over MII as an RX error. So why do we need to do this? Particularly in 100 base T1, there's the link state machine has a timeout of 200 milliseconds before it will actually change to link down. If we think about this, let's say we had a camera connected over this 100 base T1, and that's running at 20 hertz. We could lose 2 or 3 camera frames before the link down actually triggers and shows up in diagnostic logs. Sorry, one second, let me go back to this slide. The 1,000 base T1 also has a timeout in the link state monitor. However, it also has a PMA watchdog feature, and this similarly will trip much quicker. So we really need to have prompt access to this information, which brings up a topic about how we can both get the information quickly and efficiently. So if we, one way to do this might be that we would just ask for the link state faster and faster, so poll for it. Typically, we might want to do this at 1 hertz or slower. Yet, how would we then see a link down of, say, 500 milliseconds? So we might not see it due to aliasing. So we get into this loop where it's like, well, we want to look more and more quickly. So maybe we poll at 10 hertz, or maybe we poll at 100 hertz in order to see that 10 millisecond link down that's our goal. And I'm sure somebody in the audience is thinking inside, well, that sounds wildly inefficient. Why would we write our firmware that way? And we completely agree. And so this is where it becomes really important to have other mechanisms to access this information, like link state interrupts or counters that are already set up for this, like a link state change instead of just a link state. So it sounds like we have everything we need, right? And we should be good to go. But then we need to look at how the access to these linked data pieces are defined. It turns out that in most cases, they're fairly implementation specific to the driver or the firmware. So in here we have that shown as, say, like the application is running on top of the driver on the CPU or MCU on the far right. And all of the information that we're looking for is shown in blue, meaning that it's implementation specific. And the underlying information we want to get to in green is information that's standardized by 802.3. Notably, in order to get to all of the standard information we want, we need to pass through a non-standard or kind of beyond the standard interface to get to it. And so it's really important that that plumbing exists all the way through. So there's two additional details that we wanted to point out. One of them is I referred earlier to a link state interrupt, and that's actually shown here in blue because that's not completely defined in the standard. And then the other one is that it's quite common now to have the PHY directly integrated inside of, say, an Ethernet switch. I think we probably have components like that floating all around us. And when that happens, it can farther complicate whether the right interfaces exist in like the SDK or BSP. So quick note about SQI, because some might have noticed that we showed that in blue on the last slide. So we wanted to explain it a little bit. This is partly because it's Open Alliance instead of IEEE, and we're all here talking about IEEE today. It's also because we've seen some differences between what we expected from the behavior and what's actually been implemented. We think this has to do with exactly how implementations take into account interruptions to the data flow and whether that ends up in the mean square error. Generally speaking, we found this to be a better indicator for things like electrical noise around the system and not necessarily harness faults like loose pins. So rolling this all up into a set of ECU requirements, how does this look? We start with some basic metric availability requirements that you should have a link state change count, RX error, and SQI. And so we have some internal standards that require that this is available from each one of our ECUs. And then we also have a threshold built on top of that for detecting loss of signal for any losses that are longer than 10 milliseconds. And so that was the second and third category we talked about earlier. Of course, with any introduction of requirements, we also need to be able to verify those. And so we've ended up building some tools in-house to do that, which Anneka can tell us about.
Cool. Thank you so much, Ian. OK, so Ian just told us about some requirements for our ECU system. So how do we go about testing these requirements? In order to do that, we need a tool that will allow us to simulate short wire disconnects on an automotive Ethernet channel. So this could look like opening a circuit on one line of a differential pair, but it could also look like opening both lines of a differential pair simultaneously. Either way, this isn't a common capability of a lot of automotive Ethernet tools that we commonly use, like media converters or traffic generators, so we decided to make our own tool. So where do we start when we're making this tool? The first thing that we need to consider is that we need this board to sit in series with existing automotive Ethernet harnesses. So we need to choose a convenient breakout connector. For our particular use case, we decided to inform this decision based on traffic generator tools that we already use at Zūks, which was an RJ45 classic Ethernet connector. So this decision was relatively easy. The other thing that we need to consider is how do we open the circuit? There are a bunch of different ways that we could go about doing this. The two major things that we have to consider here are, one, we need a fault injector that will allow us to open the circuit fast enough to create disconnects in the area of interest that Ian previously talked about, so our transient, short, and long disconnects. But we also need a fault injector that doesn't add too much closed-loop interference when the board sits in line with the normal automotive Ethernet harness and we're not trying to inject disconnects. So we can measure things like this with the bit error rate or packet drops, byte drops, those sorts of things. So we evaluated a number of different muxes and relays, and we ended up on a final design. So this is our layer 1 fault injector tool. It is able to inject physical layer disconnects on the order of as short as 1 millisecond. We decided to use read relays for this due to their fast switching time as well as their minimal added closed loop interference. Our default board population for this allows for simultaneous disconnects on both lines of a differential pair, but we also have an alternative assembly that allows for an injected disconnect on just one of those lines. The board is able to inject faults on up to 8 Ethernet lines simultaneously, but we built it in a rather modular Eurocard design so that we can scale and inject on many, many different Ethernet channels at the same time. The last thing that was important about this board is that it needed to be within the automotive spec for 100 and 1000 base T1. So what does it look like for the board to be within that spec? So there are 2 primary things that we looked at to make sure we were in the IEEE spec for this board for the automotive Ethernet cable. We looked at return loss and we looked at insertion loss. And so for reference, if we're looking at either of these plots here, the automotive Ethernet specs are shown in white. The 100 base T1 is the dashed line and the solid line is our 1000 base T1. So insertion loss is a measure of transmitted power to incident power. It's a ratio, and we can see this represented with the transmission coefficient. So we want high transmission for our signal, so we want to be above the line. So we're looking at the left plot right now. And we can see that for all our reference cases, as well as our fault injector board, we are well above the Ethernet spec for our transmission coefficient, so it's all smooth sailing there. Now, if we move over to the right side of the plot, we're looking at return loss. So this is a ratio of our reflected power to our incident power. We want low reflection, so we want to be below the Ethernet spec for this particular metric. And as we can see, if we look at the plot, so the green and yellow reference lines are for our reference cables, and we'll see that these remain within the spec for the entire frequency range. Whereas if we look at our reference coupler as well as our fault injector board is pictured in red, we'll see that there are some minor deviations, slight excess of the Ethernet spec. While this is not ideal for return loss, we will only be using these tools on stationary test assets. So we decided that for our purposes, this was adequate. This is a bit of a side tangent, but one thing that we did want to emphasize while we were doing this testing, first we decided to evaluate some of the cables that we were doing testing on to see where they fell within the Ethernet spec. And one thing we wanted to emphasize was that all RJ45 cables are not created equal. You can't just grab something off the desk because it's convenient and it fits into the connector housing that you're using. So Cat5 cables, for example, don't even meet the 100 base T1 spec, never mind the 1000 base T1 spec. And even a Cat6A cable does not meet the 1000 base T1 spec. So please be considerate when you're picking the cabling and connectors that you're using for your testing. Okay, so now that we have a tool, we can use it to test some of our ECUs. So we conducted a series of different tests where we injected disconnects from a range of 1 millisecond to 1 second, and we monitored the different metrics that Ian was talking about previously, so link state change, receive errors, as well as SQI, to see which one of these was the best representation of these short disconnects that we are injecting. So one thing that we'll see for both 100 and 1000 base T1 for this particular ECU, the link state change was the most reliable indicator of the short injected disconnects, and as we might have predicted, as the disconnect gets longer, the link state change becomes more reliable, and as we approach shorter disconnects, 100 millisecond range for the 100 base T1, and 1 millisecond range for 1000 base T1, it becomes more unreliable. Now, one thing that we found surprising is when we look at the receive errors, we see pretty much no indication of the link going down of these disconnects with the receive errors, which we found particularly surprising for the 1 second disconnect. And another thing, if we look at the SQI, so SQI ranges from 0 to 7, 7 being the highest link quality, we notice that there's an inverse relationship between the length of the disconnect that we inject and the SQI. So this is all specific to one ECU that we tested, but we also tested another ECU, and we found some different results. So again, the link state change is relatively reliable for both 100 base T1 and 1000 base T1, and is more reliable when we get to longer disconnects. But one thing that we found that was totally different from the previous ECU was that the receive errors were actually the most reliable indicator of these short disconnects happening for this particular ECU. The SQI, however, in this particular circumstance, seemed to show no correlation to the length of the disconnects. So as you can see, the results from our first ECU and our last ECU are very different. So in summary, the mechanism to detect very short link faults is present in the IEEE Automotive Ethernet spec for both 100 and 1000 base T1. And we do appreciate when we're doing testing the ability to access these metrics in an efficient manner. However, the link detection plumbing for these components is a little unclear when we, the link detection plumbing for these components is a little bit unclear especially for highly integrated components such as switches. Fault visibility implementation is super specific to the ECU, and it should be verified per ECU. So as we saw in the last few slides, different metrics can be more reliable indicators depending on the implementation. Ooh, did I do that? We're almost done. Okay. So let's see. Talk about fault visibility. Yes, so it is really important when we're designing these systems and implementing them that we test them before we roll them out. And the last thing I'll say is that tools to validate these metrics are well within reach, as we proved with our tool that we threw together. And we would welcome seeing this sort of fault injection on more automotive Ethernet tools going forward in the future. So that will be all from us. Thank you very much. And if we have time for questions, Ian will come back.
So thank you for the presentation. So any questions?
Hello, I have one question. Thank you very much for the presentation, really interesting. So I would like to know, once you have this data, you said that you want to prevent the servicing of the car and prevent errors. So all this data, I don't know, the SQI or the RX server, you send it to the cloud to monitor it, the cars in real time. How often? How many data do you need to make it happen? This prevention.
Is this one? OK, perfect. Yes, thanks for asking about where this data actually goes to. So we didn't detail that too much in this presentation, though. This does, yes, a lot of the purpose is that this connects up to other data gathering pipelines that we have in the vehicle. So generally, yeah, it will be logged in the vehicle, and then the logs will be collected, and then they get processed in the cloud, as you're asking. And from there, we can build, for example, dashboards that we can review as like overall fleet health, or look at in focus groups. And those are all pieces of like data infrastructure that we generally have at Zūks already. So we kind of plug into that existing infrastructure. Generally speaking, like the physical layer metrics that we collect are relatively small compared to some of the other logging products that we have. So there hasn't been a ton of discussion about storage of those metrics in lifetime and such.
Okay. And one second question, if I may.
Yeah.
You showed the layer structure at one time, and you talk about application, physical layer, and you mentioned that there can be other errors in other parts of the. No.
Oh, I think yes.
At the beginning. At the beginning, yes. So do you also look for errors below the physical layer?
Yes, there is a middle category I kind of glossed over here. So like layer 3 to 5 in the OS and the IP stack. And yes, those are actually there because we also do have monitoring for things like buffer overruns and any indicator that might come from the driver implementations. And those get even like kind of like what we were seeing on that other slide where that all becomes very OS specific. So it depends on whether we're looking at like a Linux, like what flavor of Linux system, or if we're looking at like a bare metal ECU implementation or a framework based ECU. Yeah. So also sort of we wanted to mention it to recognize that this is also an important layer, though it's a bit outside of the scope of the presentation. Yeah.
For sure. Yeah. But that is interesting for the whole picture.
Yep,
Thank you very
definitely.
much.
Thank you.
Hello?
Hello.
Yeah. Two quick remarks. My name is Philipp Axer from Exxon. I've been working as a PHY architect for some time. So I think you have a misconception on what this TX error, RX error thing does. It's really just a transparent tunnel from one Mac to the other Mac, so it doesn't give you any indication on what the link is doing. And the second is the link status is sometimes deliberately kept up for some time because you have events like ESD or EMI, which are like tampering with the link quality. So the PHYs keep trying to establish link without losing it while it's not really available. So that's probably what you are seeing. So that's something which is done not by accident, but it's really on purpose.
Certainly, yeah. I think there's definitely like good reasons to have timeouts and to not immediately trip, right? So I think it's what we're looking at here is to make sure that like if the state machine has really decided that the link should go down, that it's not suitable anymore, that we see that if it really is the real state. I think what we found is that there's a fairly large gap between when this might happen and it just doesn't get detected anyways. Like we're talking like if we're in the tens of milliseconds to even sometimes like the link has been down for 100 milliseconds and we still don't see it in the logs. I think this is where we're looking.
Really, if you look at EMI testing and so on, so that's where these numbers come from. You should also look at PHY registers. It seems that you are looking a lot of like Mac level things. There, depending what kind of vendors you're working with, there's a lot of like low-level stuff which you can read out, which is exceeding by far the 823 spec. So there you might find additional things.
Oh yes, definitely. I think like if we can, I think that's a great point. In if there is additional support for registers that we can look at, we're very interested in taking those where we can. We have a number of different. PHY implementations across our devices. And so this is mostly talking about the things that are common across all the implementations. Sweet. Yeah, thank you. Perfect.
Okay, so I will ask another question. When I see this stack here, or these layers here, you will find when there is a physical problem, so a problem on the physical layer for sure, also errors on the higher layers, right? So did you dig into all the different failure mode patterns you may have seen across this stack? And can you explain all the failure mode combinations you may have seen across those stacks? Or are there also obstacles you will really have to dig into to understand what's going on? So for example, you see some dropout on layer 3 to 5 or something, and down on layer 1 and 2, there may happen something, but things don't seem to fit together. Have you seen some obstacles there, or could you explain all the things you've seen with the things you measured?
Is the question around like, do we end up with some mystery cases where we might not see exactly what's happening? I think, to be fairly direct, there are a lot of this work is coming from reaching those mystery cases so we have quite a few. We log what we can off of the vehicles that are running, and we have a lot of opportunity to increase add more over time, and then send that out and run it. And yes, this work is directly coming from situations where we get a ticket that kind of looks like the one that we're talking about here, and then we look at the breadcrumbs and can't really tell what's going on, and so we'll usually then try to add whatever diagnostics we can to pinpoint the issue. And so typically that's what's happening here that might cause us to go in and add more and more diagnostics if we can.
Okay.
Yeah.
And do you also plan to roll this, let's say, this type of mechanism out to 10-base-T1S, for example? Because there you have a multi-job bus, and you may see even other things you don't see here yet.
Yeah, this is fair. So like this one again is kind of mostly talking about these 100 and 1000 base T1, and we do have other physical layers in the vehicle, and generally, yes, we wish to have a similar layer of diagnostics for all of the different physical layers. Yeah.
I'm waiting for 10-base-T1. I've got some years to go to implement it.
Perfect. Thanks. Okay.
So
Turn back to you. Thank you.
Thank you for the presentation.